Okay, remember, physical layer deals with devices, the physical devices on the network and the media, the cables, right? And everything is encoded into ones and zeros. Data link deals with frames, MAC addresses, and switches are on work on layer 2. Right, then on the network layer, we have packets, IP addresses, and routers. Routers will still use data link layer, but for purposes of finding the best path on the network, they're going to be using IP addresses. And then we're not going to go through the other layers on the top because right now we're only going to deal with these layers. Next thing to remember, I asked you to visualize the PDUs, protocol data units, as envelopes. As the PDU travels to the different layers, each layer is going to add different labels or fields to the PDU. And actual ones and zeros might look something like this. Here's your data. Then your presentation layer might add a little bit more code at the beginning of your code and at the end of the code. Then a session might add more information, and this is how you're encapsulating the information. Here's your data that you started with. Here's the data that gets added to by the presentation layer. Here's the data that gets added by the session layer, and so on and so on. But again, you can visualize it like an envelope. That envelope gets placed inside a new envelope as it goes to a new layer, and then information for specific to that layer gets added to it. Then it's placed into a new layer, a new envelope, and moved on to a new layer, and until it gets to the physical layer where it gets encoded to ones and zeros. Another thing we spoke about was how the MAC address gets changed as the frame moves throughout the network. So let's go over that real quickly. This computer's IP, we're gonna say is 1.1, and the MAC address is AA. That's just an example, right? And then it's gonna send information to another computer, and maybe in a different network. The MAC address, the IP address for this computer might be 11.99, and let's say the MAC address could be CCNA. Just an example. First of all, at the network layer is going to add the IP address. So this is my frame. And the IP, source IP address is going to be 1.1. And then it's going to IP address 11.99. So here is going to add 11.99. When it moves down to data link layer, the data link is going to add the source MAC address. But for the destination, let's say it's connecting to a router, and this router is going to be BB6A MAC address. For the destination, is going to add the router's MAC address, BB6A. And then it's going to send it out, encode it, and send it out to the router. The router is going to receive this. Layer 3 is going to read the IP address and then send it back to layer 2 to add a new MAC address for the source and a new MAC address for the destination. Let's say this one has 1B C8 MAC address. And again, it's just an example. All right, so the new frame is gonna have for the source BB6A. The IP address at layer 3 is gonna stay exactly the same. Sorry, 6A. Destination is gonna be 1B C8. All right, so this saying is going from this router to this router. And then it's gonna send it to layer 1 and encode it and send it out through the interface going to router, let's call this one router 1, router 2. All right, once it gets to router 2 is gonna decode the 1s and 0s, send the frame out to layer 2. Layer 2 is gonna send the frame to layer 3. The layer 3 is gonna look at the IP address, which is gonna stay the same. 1.1 is gonna be the source, and 11.99 is gonna be the destination. So once it's gonna read the IP address so it can find the best path, because this router might be connected to other routers. And it needs to know where this frame is going. Which network is it going to? Is it going to network A or network B? To figure this out, it's gonna need the IP address and subnet mask. Once it knows which network is going to, it's gonna place that layer 3 frame, that layer 3 packet inside a new envelope, send it to the layer 2 data link layer, and add a new MAC address. This is gonna be the 1BC8, the MAC address of the device that currently has the frame. And then the MAC address of the device that is gonna immediately receive the frame right after this device, which in this case is gonna be our final destination, CCNA8. And then it's gonna again encode that frame into 1s and 0s. The encoding signal is gonna depend on whether you're using Ethernet or fiber or wireless. But it's gonna send the signals, and eventually this computer is gonna receive the frame, is gonna decode the 1s and 0s, and then up each layer until it gets to the application layer. Okay, that should be enough of a refresher. Let's move on to chapter 6. And this is all about the data link layer. Now, one thing we're gonna see is that the data link layer has 2 sublayers, the LLC layer, sublayer, and the MAC sublayer. All right, so let's get started. The data link layer is responsible for NIC to NIC communication. So like you saw in the previous example, as it moves from one network card to another network card in the same network, the MAC address on the frame is going to change. It enables upper layers to use the physical media to communicate. It encapsulates layer 3 packets into layer 2 frames, controls how data is placed and received on the media, performs error detection, and we'll talk more about that in a bit, de-encapsulates layer 2 frames, and you might see the word node on the next slides. A node is a device that can receive, create, store, or forward data. All right, and here's another representation of what's happening as the data or the PDUs travel from one layer to another layer. And remember that on each layer, the PDU might have a different name. The top 3 layers are going to call it data, then segment on layer 4, packet layer 3, and frame layer 2, and bits at layer 1, where everything is encoded into different signals that are going to represent 1s and 0s. Okay, so and here I want you to look at the labels. Just remember that each layer is going to add its own labels or fields to the PDU as it's traveling through the device. IEEE 802 local area networks and municipal area networks. Municipal area network is something like a university campus that has different buildings connected to the same network. It's not quite a wide area network yet. Logical link control LLC is one of the sublayers that you will find on the data link layer. The LLC communicates between layer 3 and layer 1. It identifies which layer protocol is being used on the network. So if you're using IPv4 and IPv6, this is one of the jobs of the sublayer to identify what you're using. It'll communicate with layer 3 and ask, are you using IPv4 or are you using IPv6? It will also allow IPv4 and IPv6 to use the same network card and media, the same network physical cables that connect the network. Then you have media access control MAC sublayer. It's in charge of the MAC addressing. So when you're adding the labels of the source MAC address and destination MAC address, the media access control sublayer is dealing with that. It implements IEEE 802.3 and 802.11, 802.3, 802.11, or 802.15 standards to control the hardware responsible for interacting with the wired optical or wireless transmission media. Again, the MAC sublayer controls the NIC and other hardware that is responsible for sending and receiving data on the wired or wireless local area networks or municipal area networks. So encapsulation includes the following when you're in the media access control layer, sublayer: frame delimiting, addressing, and error detection. Frame delimiting provides important delimiters to identify fields within a frame. A delimiter is going to be like a character or a code that marks the beginning or the end of the data. In this case, it's going to be the beginning or the end of the frame. Addressing, when encapsulating the frame, this is where addressing happens. So the source MAC address is added and the destination MAC address. And it will change depending on what network you're in or what device it's going to. Error detection happens in this layer too. It includes a trailer used to detect transmission errors, and we'll go over that in a little bit. This sublayer also controls communication in a shared half duplex medium. So you have half duplex and full duplex. Half duplex means that if you have two devices, they can't communicate both at the same time in the same network. Full duplex, in a full duplex network, the devices can send and receive information at the same time. All right, so each hop along the path, and we're talking from one device to another one, that's going to be a hop. At each hop along the path, a router performs the following: accepts the frame from the medium, de-encapsulates the frame, re-encapsulates the packet into a new frame, forwards the new frame appropriately through the medium. Forwards the new frame appropriate to the median. So if it's supposed to be a wireless signal or a fiber signal, is going to encode it to whatever signals it needs for that medium. Which again, medium, we're talking about the technology used to transfer the information. So if it's fiber or wireless or electrical signals. This is an example of the steps that happen when the router 1 receives the first frame. And I already went over it, but here it is one more time. The router receives encoded bits at layer 1 through the NIC card. The network card decodes the bits into frames. Layer 2 receives the frame or envelope, if you want to imagine it like that. Layer 2 forwards the frame to layer 3. Layer 3 opens the envelope and takes out the packet. Layer 3 reads the source and destination IP address labels on the packet. It is going to use this IP address to find the best path through the network to the destination. Once it finds the path to the destination, places the packet into a new envelope and forwards it to layer 2. Layer 2 adds the new labels to the frame with the new source and destination MAC addresses. Layer 2 then forwards the frame, which gets encoded into bits and sent out through the interface to the next device. All right, now we're talking about the different types of topologies. You have, again, there's something that we covered in chapter 2, I believe, chapter 2 or 3. Physical topology identifies the physical connections and how the devices are connected. It identifies room numbers and locations on the equipment rack. Logical topology identifies virtual connections using device interfaces and layer 3 IP addressing schemes. Right now, you don't need to understand what virtual connections means. Just know what the difference is between physical and logical topologies. The data link layer sees the logical topology of the network. What it's saying here is that the data link is going to pay attention to the logical topology of the network, not just the physical. So different topologies, and these are for wide area networks. You have point-to-point topologies. There's a permanent link between two endpoints. So one router directly connected to another router with a cable. Or it could be maybe going from one building to another one. So you might have a router in one building, and then you might have another router in another building, and a fiber cable connecting both of them. Hub and spoke. And you haven't seen the star topology yet, but this is a wide area network version of the star topology. All the different devices are connected to one central device. In the example here, you have branch A, branch B, branch C, and branch D. Everything's connected to branch A. And if D wants to talk to B, it has to go through A. All right? The devices cannot communicate straight to branch D. This is known as hub and spoke topology. When using the mesh topology, you will have high availability because if one device fails, the other devices can still communicate with each other. Even though this is a better topology, it is more costly and difficult to manage because you have a lot more connections to worry about. Then you have the star topology and local area networks. You have one device in the center, like a switch, and all the computers connected to that one device. Again, on a wide area network is known as hub and spoke. Local area networks, star topology. All right, then you have the ring topology. This is a legacy topology. All the devices would be chained together, and then a token would be which would be a signal that would go around, would tell the devices when each one of them could communicate. They all had to wait until they received the token. There's something in the book that is talking about how point-to-point connection can have different devices in the center, but if you have a logical point-to-point, the end devices are not going to see the intermediary devices in the middle. Physical point-to-point, two nodes that do not share the media with other hosts. So there's one cable and no other devices connected to that cable other than the devices sending and receiving, two devices. Logical data link protocols can be simple. This is saying that the protocols on the logical layer can be simple because the labels or fields that you're going to add to a physical point-to-point connection are not going to be as many as if you were using logical point-to-point. It's going to use other protocols and more information. In a logical point-to-point topology, a source and destination node can be indirectly connected through multiple devices. The physical devices in the network do not affect the logical topology, meaning that the end devices that are communicating with each other will see the connections through the network as if there were no intermediary devices. All right, so this is what might be happening. You might have different devices in between connecting the networks, but if you have a logical point-to-point, this is what the end devices are gonna see. One connection from one device to the other one. You have LAN topologies, local area network topologies. We already covered some of them. We have the star topology, which is easy to install, very scalable, and easy to troubleshoot. And then you have the extended topology, which is just an extension of that star topology. It says here very scalable, meaning that it's easy to just add a new device to the network. You have legacy topologies like the Ethernet and token ring. You have the bus topology, legacy again. Intermediary devices not required on the bus topology, terminated in some form at each end. All right, so that is this topology at the bottom left corner. All the devices will connect to one coaxial cable, and that coaxial cable would be terminated with a component at each end of the cable. This is legacy. Legacy Ethernet use coaxial. All right, I already said that. All right, then you have ring topology, which I already spoke about. No need for termination because everything is chained together, but a token is used to tell the different devices when they can communicate on the network. We spoke a little bit about half duplex and full duplex. Half duplex, in half duplex, sending and receiving cannot happen simultaneously. Is used by wireless local area networks nowadays, and legacy bus topologies back in the day. So a bus topology, again, is going to be the one that used the coaxial cable and was terminated from one side to the other one. It was terminated at the ends. All right, full duplex, both devices can simultaneously transmit and receive on the shared media. Ethernet switches are full duplex by default, but can be changed. So the switch that you'll be using, the settings on them, by default, they're set to full duplex. You need to be careful because when two devices are communicating with each other, they have to be using the same mode. If one is using half duplex, the other one has to be using half duplex. If one is using full duplex, the other one has to be full duplex. If not, there's going to be collisions. All right, access control methods that are used by the MAC sub-interface of the data link layer. Multi-access network is used by Ethernet LANs and wireless local area networks. These networks can have two or more end devices attempting to access the network simultaneously. All right, two methods used for sharing the physical media are contention-based access and controlled access. In contention-based access, all nodes operate in half duplex. The nodes compete for the use of the medium. Only one device can send at a time. There is a process if more than one device transmit at one time, and there's collisions. The methods used for contention-based access are carrier sense multiple access with collision detection, CCNA1v7, which was used for legacy bus topologies, and carrier sense multiple access with collision avoidance, CCNA1v7, used on wireless local area networks. And we're going to come back to this graphic here in a moment. All right. In controlled access, each node has its own time to use the medium. A device must wait its turn to access the medium. And this is talking about CCNA with collision avoidance. Controlled access. Again, we have contention-based access and controlled access, the two methods of sharing the physical media. We spoke about contention-based access. Now let's go to controlled access. In controlled access, each node has its own time to use the medium. A device must wait its turn to access the medium. So for example, token ring topology. In a token ring topology, there was a token that would go, a signal that would be sent through the network, and each device would have to wait for that signal to send information to the network. And then there's another type of network, ArcNet, which is also legacy, that used to use this controlled access. Both of them legacy, replaced by newer technology. All right, we have contention-based access, CCNA, collision detection, remember that. Examples of contention-based access, again, wireless local area networks use CCNA, CA. legacy bus topology Ethernet LANs, and legacy Ethernet local area networks using a hub use CCNA collision detection, same as the bus topology. And a hub is just gonna be a device that splits the signal. Sorry, behind this hub, there's a cable connecting it to the internet. Well, that cable, the signal for that cable is split into these 3 cables going through these 3 different computers. So in reality, these 3 computers are sharing the same cable. And this is what it's talking about here, where it says legacy Ethernet local area networks using a hub. These networks operate at half duplex. If 2 devices transmit at the same time, a collision will occur. The data will be corrupted and will need to be resent. Right? Collision avoidance method. 802.11 wireless local area networks use collision avoidance. Collision avoidance uses a method similar to collision detection to detect if the media is clear, but it also uses other techniques. It does not detect collisions, it tries to avoid them. So the main job is to try to avoid them. Each device that transmits includes the time and duration that it needs to transmit for. All other devices receive the transmission and will know how long the medium will be unavailable. Contention-based access does not scale under heavy media access. So both CA and CD do not scale well when many devices are on the same network. So the more devices you add to the network, the slower the network's gonna get, the more collisions that there will be. And here's an example of what happens in the collision avoidance. Let's say this wireless router here is about to send a message to computer A. It's gonna send a broadcast to all the computers on the network saying, I'm about to send a message for, it's gonna take me around 10 milliseconds to complete the transfer. And the other devices are gonna reply, computer A is gonna say, okay, I'll be waiting for the message. The other devices will say, okay, I will wait, I will not send anything until 10 milliseconds have passed. Just an example or a way to visualize what we just spoke about. All right, so now we're gonna talk about the different fields that are located on a frame. And a frame, again, is the envelope that you will get on a data link layer. The information appended to the frame is determined by the protocol being used. So first, appended to the frame, meaning the label that you're gonna add to the frame or the field, the information that you're gonna add to this frame is determined by the whatever protocol you're using at the time. The data link layer encodes the packet that it receives from layer 3 with the information, whether it's IPv4 or IPv6, is gonna encapsulate it with a header and trailer. Okay, this is the information that you add at the beginning or at the end of the information that it received from the data, from the networking layer, from layer 3. Okay, it's gonna add a header and a trailer. The data link layer is responsible for NIC-to-NIC communication within the same network. We covered that already. The 3 basic parts of the frame include the header, the data that it received from the layer 3 network, from the layer 3, and the trailer. Okay, the structure of the frame and the fields contained in the header and the trailer vary according to the protocol. So again, depending on what kind of media you're gonna be sending the information through, or whether it's IPv4 or IPv6, the fields or the information that is added to this frame is gonna be different. The amount of control information needed in the frame varies to match the access control requirements of the media. So meaning the requirements, if it has to be encoded into light signals or has to be encoded into electrical signals, radio wave signals, each one of those, that's what we're talking about when we're talking about requirements of the media and logical topology. So again, the amount of control information needed in the frame varies to match the access control requirements, right? The information you're gonna add, the labels you're gonna add to that envelope, the fields you're gonna add to the header and trailer. For example, a wireless local network frame must include procedures for collision avoidance. These frames will include more information on the header compared to Ethernet frames. So remember that wireless uses collision avoidance and is half duplex. An Ethernet frame is not gonna be using the same protocols. So they're not gonna use the same information on that frame. Hopefully that helps a little bit. All right, the different fields on a frame, and there's more fields, but there's the basic ones. Again, the data this is gonna be the information we received from layer 3, the packet. This is gonna be encapsulated with a header at the beginning and a trailer at the end. When it leaves the network and is received by the other device is gonna receive the header first, then the data, then the trailer. The following is how the error detection is done. The device that is sending the information will use an equation to create a summary of the contents of the frame. So everything that's gonna be sent, everything that's here and the header and the data and the trailer, at the very end of the trailer, there's gonna be a code that's gonna summarize everything that's here. The summary is known as the cyclic redundancy check value, CRC value. This value is placed in the frame check sequence field. So in the FCS field, there's gonna be a CRC value inside the trailer. Using the FCS field in the trailer, a receiving device will be able to tell if the data is corrupted. So it will look at the code that was created, a summary of all the data that was sent. The device that is receiving the frame is going to create a new equation. It's going to do a new equation of the data that it received. That equation is going to give it a value. It's going to come out with a value. This device that received the frame is going to check the value that it created itself with the value that was sent with the frame. If the two values match, then the data is not corrupted and it is the same. If there's a discrepancy, then that means that something happened along the way. This is similar if you know about hashing when we're talking about security, is similar to that. A layer 2 address, layer 2 addresses, right? Layer 2 addresses are physical addresses. The MAC addresses are contained within the header at the beginning of the frame. This is where you put the source and destination MAC address. So the receiving device can quickly decide whether the frame is addressed to it before processing the rest of the frame. So as soon as the device receives the header, it's gonna check the destination MAC address. And if it's the same one that belongs to that device, then it's gonna continue to process the frame. If it isn't, then it's gonna, depending on which device it is, if it's a computer, for example, it's just gonna destroy the frame or not continue to process the frame. MAC addresses do not indicate what network the device is located in. It's only used for local delivery. If the data must leave the local network, a device such as a router must be used, and that router is gonna need an IP address and subnet mask to be able to identify what network it is supposed to be going to. Local area networks and wide area network frames. Ethernet protocols are used by local area networks. Wireless local area networks use IEEE 802.11 protocols. When you're buying a wireless device, it might say something like IEEE 802.11a, .11b, .11ac, .11g, all right? Those are the different protocols used for wireless communications. The protocols used for wide area networks include point-to-point protocols, high-level data link protocols, frame relay, asynchronous transfer mode protocols, and X.225. We'll learn more about these protocols on the later chapters, on the later courses, CCNA 2 and 3. These layer 2 protocols used by wide area networks are now being replaced by Ethernet protocols. A number of devices use layer 2 protocols. Devices like network cards on computers, interfaces on routers, and layer 2 switches. The protocol use depends on the technology used in the topology. Again, fiber, electrical signals, or wireless. The difference in bandwidth normally results in the use of different protocols for LANs and WANs, wide area networks. And an example of that, let's go to the animation on the book. You can see here as information travels, might travel through wireless or travel through wide area links, wide area networks, go through the internet, and then back to Ethernet. As it changes from one protocol to the other one, each protocol is gonna have different information added to the frame. Some might take longer than others, and this is gonna cause different bandwidths along the path. Different delays along the path that might slow down the network. And that should be the end of this chapter.